Just let me know.
Wonderful. So why don't you take it away?
Okay, great. Hi everyone, I'm Ipek, and today I'll be presenting my project called Inferring Level Progress in Goal-Directed and Open-Ended Tasks. This presentation in many ways is a proposal to turn this work into a big team science project. So I want to start with one question. How do we know if a learner is truly making progress? So how do you know Sorry, there's a bar. Okay. How do you know when you're finally getting better at playing the piano, learning chess, or practicing a sport? Is it when you succeed once or when you notice steady progress? Or let's say you imagine watching a child learning to ride a bike. They wobble, fall, get back up, and try again. At what point do you say, yes, they're finally learning now? Or you watch a friend play a video game. What makes you think that they're actually improving? Is it when they beat harder levels or when they just keep trying the same one? In a similar logic, why do fitness apps and language learning platforms keep showing us these milestones and progress bars? Because seeing a clear goal makes every step feel more meaningful. So, 2 summers ago, I started working at the Cognitive Development and Learning Lab at UC Berkeley, where we worked on this study called the Automated Curriculum Learning Study, in which children played a multi-level game. So I'm going to start with the basic insight that we started with, which was that from early childhood, humans can create a causal curriculum to reach a goal that is too challenging to attain in a single attempt. So what does this really mean? Let's first talk about what curriculum learning means. Curriculum learning is a machine learning technique where training data is presented to a model in a structured, progressive way, starting with simpler examples and gradually increasing complexity as the model improves. So this approach is inspired by human learning, as humans also learn by mastering basic concepts before tackling more complex ones. So one example of this is like babies start speaking by babbling. They just like make these random noises, and they then start learning basic words which they combine to make sentences in the later phase, and then they start writing essays. So this is kind of like the human example of curriculum learning, where we basically improve with like steps, and there's no one single way to solve a challenging task in a single attempt. So then in our study, we made children play these series of games called Prochkin environments, which are a series of procedurally generated environments that are used to benchmark reinforcement learning. So it's like a series of multi-level games. And we specifically in our study made them play this game called the Leaper, which you might also know as Frogger, I think. Where basically they were playing this frog, which is supposed to cross from one side of the river to the other side. And every single level, the number of lanes increases. So the frog has to jump on the leaves, and if it falls into the water, the game ends. So in level 1, there's only 1 lane. Level 2, there's 3 lanes, 5 and 7. And we basically would make the kids play one of these levels and then ask them, okay, which level do you want to go to next? So they would have the freedom to make the choice of like which level they want to play next, and they can either go back to a previous level, stay on the same level, or move to an upper level. So we were kind of like trying to see, okay, they just played level 2 and they lost. Are they gonna stay on level 2, or are they gonna like go back to an easier level so they can practice, or even go up to a higher level, which means that they can't really build that causal curriculum that I just described. And so to go over the results, we found that when children felt less competent at a level, they tended to repeat it or drop to an easier one. And when they felt confident, they moved up. So the bar chart here shows how often children move to a harder or easier level depending on their completion rate. And by completion rate, I mean how many of the like lanes were they able to get in like a single level. So if they were below 50% competent, they often retreated to easier levels, which you can see here in the green box, which shows like staying on the same level. Orange is returning to like 1 level below or returning to 2 levels below. And if they were between 50 and 75%, they usually stayed on the same level. They stayed put. And if they were about 75%, they usually advanced. So this kind of this tells us that children are monitoring their own learning progress and using it to guide their next step. So they basically systematically design their own curricula to tackle a challenging game task. So before we move on to the next discussion, let's also talk about why level competence, which is basically knowing what your current progress is important. So it's a measure of performance in a particular skill or ability, and it represents the degree to which an individual can successfully perform a task or demonstrate a skill at a certain level of expertise. And in our study, we found that the 5 to 7-year-old children actively use their current level competence to determine their next step in the curriculum and make improvements to their performance during this process as a result. So again, to bring us back to the conclusions, we found that children use their level competence to decide the next step. And this ability to self-monitor their progress and adjust based on like their current success level helps them make real improvements in their performance. And so to bring us to the next study, we can design agents, reinforcement learning agents, that use level competence as a reward signal too, and what differences it's going to make in their performance. So again, thinking about how children treat their level competence as an intrinsic reward and are motivated to master easier levels in order to do better at the more difficult ones, we can use this human capability for learning as an additional experiment where also reinforcement learning agents use level competence as an auxiliary reward. And to define what an auxiliary reward is, it's basically an additional reward signal provided to the agent that we train the agent with. And it's used to improve the learning in the training progress. So when we did that, we found the following results. Let me go over the graphs. The red line shows where the task difficulty increases. So for example, the number of lanes is increasing, and around the red line, you can see that the extrinsic reward drops sharply. This is called catastrophic forgetting, which is a phenomenon where an AI model, after learning a new task or data, experiences a significant and abrupt loss of the previously learned knowledge. So it basically forgets about its own progress. And the green line, which represents the intrinsic reward, stays stable or increases slightly, indicating that the agent is still receiving some guidance through intrinsic motivation or level competence, even when extrinsic rewards drop. So eventually extrinsic rewards begin to rise again, showing recovery due to the intrinsic reward keeping the learning signal alive. So what does this mean? Basically adding an intrinsic reward based on level competence, so training the model with level competence as the auxiliary reward, helps the agent avoid long-term divergence, which is again also a failure to learn, and recover from these sudden drops in performance when the difficulty increases. So what does this really imply? Basically, the baseline curriculum where the agents are just trained with the hand-designed easiest to hardest schedule, they consistently fail, versus when we add level competence as a reward, when we train the models with this as an auxiliary reward, the catastrophic forgetting effect goes away and the model can generalize to the target task. So again, we can conclude that learners, both humans and reinforcement learning agents, build their own sequence of tasks to master complex goals. And so reframing this question, we asked a new question. We know from earlier studies that learners can decide which level they want to play next based on their level competence. But how do outside observers judge competence and learning progress when they watch someone else move through levels? So what does this exactly mean? We call this study the level learning progress study. And the main question was that how do people perceive another agents and other players' learning trajectory? And so in this study, participants were this time external observers and not players of the game. And they had to infer how much progress a player was making based on level transitions. So this could tell us what signals humans to use to evaluate competence and improvement. And by understanding how humans infer learning progress, again, we can design reinforcement learning agents that use similar heuristics in their own curriculum learning. So to describe the study, we basically had this Leaper or Frogger game again, but this time, instead of making the participants play the game, we would give them screenshots from the game and tell them the kid starts from level 1, so they had to like observe this kid playing the game, but not watch the kid. So they wouldn't know how much like progress the kid made in a level. They just would know what level the kid is playing. And then we would tell them, okay, after playing level 1, the player chooses to play level 1 again. And then we would ask them, how much of level 1 do you think the player completed based on this like the progress transition that we just showed them? And then we would ask them for an explanation. And we also had 2 versions to the study. Sorry. So in one of the versions, we told them at the beginning of the game that the kid is eventually playing to win level 3, which is the goal level, versus we told them there's like no goal level, which is the open-ended condition. And so in the goal level version, we also had this additional question, which was that if the player were to play, like after making this transition from level 1 to level 1, if the player were to play the goal level, which is level 3, how many of the logs do you think they would be able to complete? So we would just ask them to like infer a little bit if the player is capable of passing the goal level based on how much progress they've already made. And the reason why we like added or removed this explicit goal was because we wanted to test whether having a meaningful goal at the end would make a difference in our inference of understanding progress. And we also gave them this reminder at the end of every like transition. The goal of the game is for the player to complete level 3 in the goal level version of the study. So we tested all of these level transitions, basically 16 level transitions in a randomized order with all of the participants. And we just put this study on Prolific. And for the ChatGPT part, to test ChatGPT, we just pasted these questions on ChatGPT, kind of just asking ChatGPT to answer these questions as well. And we had two hypotheses. One was the goal primacy hypothesis, which states that participants' inferences differ significantly across conditions, meaning in the goal-directed condition, observers over-attributed competence when transitions move toward or beyond the target level. And in the rational strategy hypothesis, we just argued that in contrast, under open-ended conditions, participants used a more incremental, effort-based evaluation strategy. So now let's move on to the results. So understand well, we recorded all of the results. So we basically were like, okay, for the level 1 to level 1 transition, the participant inferred 0 progress. So we will put this in the 0 to 25% progress bin. And we just model all of our results. So this is for the goal level target condition, basically the question where we ask them, okay, the player just played level 1 again. How much of the first level do you think they were able to complete? And then one question for how much of the goal level do you think they're going to be able to complete? And then also modeling the no goal level study, just asking them how much progress they think the player has made. And overall, if you put these two together, this is the goal level version, this is the no goal level version, we can see that across transitions, participants infer greater progress when a goal is present. In the box plots, you can see that like with larger level jumps, the boxes in the goal condition, which is the one on the left, are in general tighter and higher. So people not only agreed more and were more consistent, but they also believed that the player had made more progress when they knew about the target. And in contrast, in the no goal condition, which is the one on the right, there's a broader and more variable distribution. So without a clear anchor, participants disagreed more about what counted as progress. So this is just like a general look at it. This is not really like analyzing the results. We then fit this to a regression model, where we basically asked, does the presence of a goal influence? So we were measuring the effect of the goal level. So I had like two predictors, one transition, which is basically the numbers of like the level jumps, and condition as the other factor that we put into this model, which was, did they have a goal or did they not have a goal? And we were measuring the progress inferred. So we found overall that the presence of a goal inflates perceived competence. So the p-value for transition was far below 0.05, which means that as transition increases, so bigger level jumps, inferred progress also increases, and participants attribute more progress when the level jump is larger. But this was obvious. We also found that the p-value for the goal level is below the significant level, which means that they inferred 7.48% more progress in the goal-directed condition controlling for transition size. So basically, when there's a goal, people overestimate the progress that they're seeing from the player. And when we did the same study with ChatGPT, which is when we just pasted these questions and also the screenshots of the game study, we again modeled all of our results for the goal and no goal conditions, and putting these two together, we saw less of a less like sensitive to the goal manipulation. Again, like you can see the difference side by side. While for humans, the goal versus no goal distributions diverged more strongly. For ChatGPT, they're nearly overlapping, and there's not that much of a difference in distribution. Again, fitting this on a regression model, we saw that each unit increase in transition causes an increase in inferred progress, which means that higher transitions suggest more learning, just like humans. But in the no goal condition, there's also a drop of 8.3 logs, but the significance level is not below, the p level is not below 0.05, meaning that without an explicit goal, participants still may underestimate the agent's progress, but the evidence is not quite strong enough to confirm this with high confidence. So this brings us to the conclusions. Humans are sensitive to goal presence. When there's a goal, we show higher progress inference. So we use the presence of a goal as a strong cue to interpret learning, and we likely think that the agent is improving toward a goal, or that transitions make sense in the context of achieving a goal, or that progress has directionality and intentionality. And this aligns with the previous research showing that humans interpret actions as goal-directed and value improvement more when there is a goal at the end. Whereas for ChatGPT, it's less sensitive to goal structure, meaning that it doesn't really use goal presence as a major cue. This is potentially because ChatGPT's token prediction doesn't internally represent goal states the way humans do, or the model might focus on level transitions or surface statistics without integrating the idea of intended outcomes. But this kind of brings us to a gap where the current LLMs lack grounded models of agency or intention, and while humans can think of these as a function of actions and goals, ChatGPT tracks transitions in more of like a structured way, and not as it doesn't really have the built-in motivational system that humans do. I'm gonna skip these for the sake of time, but this is basically, we also asked the participants, both human and large language models, for explanations, and we're kind of like analyzing, okay, like how did they interpret this progress. So to quickly go over, for the goal condition, humans said, like one participant said, it makes sense to play the same level again if you made significant progress on your previous attempt. So this kind of shows and like thinking with intent. There's a model of what the agent knows or expects, versus in the no goal condition, they just say, I believe they came close to completing the level but were unsuccessful, so they chose to try that level again. And you can see there's kind of more of a focus on performance outcome and less of a strategic reasoning. And I'm gonna skip the ones on ChatGPT for now, but basically the conclusion was that humans show a greater sensitivity to goal presence, and ChatGPT maintains more of a behavior-driven estimation pattern. And then we later scaled up the study to a 10-level study, just because I think it's nicer to try multiple or alternating goal placements and not just one goal level, or also to have like bigger level jumps, and not just like from level 1 to level 4 as the highest range. I'm also gonna skip some of the limitations for now, but again, let's bring this to how it relates to big team science. So this research brings together developmental psychology, reinforcement learning, and AI to investigate how people and systems infer learning progress in others. So that's exactly where the big team science part comes in. This kind of goes over some of our conclusions. Our study is on how humans and AI systems differ in understanding learning progress under goal-directed versus open-ended conditions. So this requires large and diverse samples, both cross-culturally, across age groups, also across different models, AI models, and different task variants. And obviously no single lab can do this alone. So I was thinking of maybe potentially calling this mini learners, where think of many learners as an open, flexible framework for studying how humans and machines understand level learning progress. So we can vary the task environment, the way goals are framed, and how progress is displayed. So kind of have variations of how to present the goal versus no goal framing. And as our early steps, the first step is obviously simplicity. We would start with a core level learning progress task using a single Prochkin game environment, and like a basic, we can scale this up to 2 human age groups and 1 AI baseline, and 2 framing conditions, again, goal versus no goal conditions, and scaling this up. So these early collaborative steps will give us the infrastructure we need to build a larger data set. And scaling this up would mean having a cross-cultural expansion, so observers in different countries, adding multiple non-game tasks, so we can introduce educational or real-world tasks like language learning, drawing, or problem solving, and multimodal comparison. So beyond ChatGPT, we could also include other AI systems, from reinforcement learning agents to multimodal models. And the goal again is to build to advance our understanding of how humans infer progress and competence, which has implications for education, evaluation, and even workplace training. And it also deepens on our understanding of AI in learning context. So by comparing humans and models, we identify where AI's reasoning about progress diverges. For example, where it tracks performance but misses purpose. And also lastly, it kind of strengthens the design of automated curriculum learning in AI. So if we can model how humans generate their own learning sequences, we can also build agents that learn in similarly structured, interpretable ways. So together, these insights help bridge the cognitive gap between human and machine learning. And for big team science, the advancements will be that multi-site data sets on how children and adults evaluate progress, which is a big contribution to developmental psychology, and shared frameworks for testing how different reward structures or training curricula reproduce human-like patterns of inference and machine learning. is another contribution. And finally, testing how humans infer hidden states like competence. We can link the theory of mind research with computational modeling, which will advance our understanding of mental state attribution in cognitive science. So there's a lot of these impacts, and obviously educational impacts, where insights into how people perceive progress could help us design curricula that's emphasizes these clear targets and milestones that are also level learning progresses, and also could give us better models of perceived competence and reskilling programs in the workplace, and transparent AI systems that communicate learning in ways humans understand and trust. So yeah, the cross lab collaboration and diversity and inclusion and open science infrastructure, I believe, are would be good ways to make this project bigger and have more data in it. And yeah, I think that big team science can work at the intersection of human and machine learning when applied to this study. But yeah, those are kind of the three pillars: developmental, computation, and cognition, that show how big team science can do what individual labs cannot, and connect human reasoning with machine reasoning on a global scale. But I'm open to any recommendations, and thank you for listening.
Great job. I had many questions, but
yeah.
I think so. You're talking about scaling up, so you're wanting to add more levels and more people. Can you go back to the scaling up?
Yeah.
So
sorry, let me go back to that slide. I was just saying in the sense that, like, so the basic study is a core like task that everyone uses, and like same age groups and same AI baseline and same kind of conditions, versus in the scaling up condition, there will be a cross-cultural expansion. So right now, the people that we tested are just like, the same set of participants on Prolific. But if we do this on a cross-cultural level, does the progress inference change? So that would, like, kind of spread the community that we're testing. And also, like, if we change the game tasks, so if it's not a game anymore, but we're making them do something language related or do something like educational, and also test different test like task variants and observer measures, kind of like vary these things that are at the foundation of this project, to see how we can like manipulate the results.
Cool. Yeah, I think it's really interesting with the comparison to like LLMs, because I've been doing some stuff with that with language. You see the same kinds of patterns of results in LLMs, but you don't, like, if I say, okay, well, let me correlate them, they're totally uncorrelated. But visually, the histogram is the same. I'm talking about priming. Show you the same, almost exact histogram on different scales, but when I get into the item by item, it just doesn't match. So I've been trying to figure out kind of what that difference is.
Yeah.
So I thought this was really interesting to see how you're doing those comparisons with training. So
yeah.
I don't know if there are any, one person popped out, but I don't know if there are any other questions. In a second, I will have to run the next one.
Yeah. No worries. Didn't even realize how 25 minutes went by.
Yeah, it does go by fast. I think you get excited because you're talking about your own work, right?
Yeah.
All right, so I'll hit stop.